Welcome to the severe weather analysis for Adelaide, South Australia. This is Wednesday, November 26, 2025, analysing the 9 a.m. local time sounding. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Looking at this morning's sounding, we are seeing an extremely stable atmosphere over Adelaide. The Skew-T diagram shows the red temperature profile and green dewpoint profile with minimal CAPE available. Mixed layer CAPE is only 24 joules per kilogram, essentially negligible for storm development. There's a small pink shaded area showing the limited CAPE between the parcel path and environmental temperature. The atmosphere is very dry, with surface dew point of 12 degrees Celsius and surface temperature of 17 degrees. The lifted condensation level sits at 670 meters above ground, which would normally be favorable, but there's simply no fuel for convection. We have minimal convective inhibition, essentially uncapped, but without energy there's nothing to release. The enhanced Skew-T shows multiple parcel analyses with the blue shaded area representing convective inhibition and pink representing CAPE. We can see the mixed layer parcel path in blue dashes, the surface parcel in red dashes, and the most unstable parcel. The atmosphere remains subconvective even with the multi-parcel analysis. The environment shows an inversion layer between 700 and 800 hectopascals, marked on the diagram. The most unstable CAPE reaches only 100 joules per kilogram, far below the threshold needed for thunderstorm development in Australian conditions. The lack of moisture through the column, shown by the wide gap between temperature and dew point, means there's insufficient water vapor to fuel any convective processes. Looking ahead to tomorrow morning, the machine learning forecast shows continued subconvective conditions. CAPE remains at 0 joules per kilogram with surface-based CAPE also at 0. However, we are seeing strong wind shear develop, with 0 to 6 km shear forecast at 28 meters per second. The lifted condensation level drops to 652 meters above ground level. The significant tornado parameter and supercell composite parameter both remain at 0.00, indicating that while the shear environment becomes more favorable, the complete absence of CAPE means storms simply cannot form. If any initiation were to occur through forced lift or other mechanisms, the shear environment would support organization, but the atmosphere lacks the fuel needed for development. By tomorrow afternoon, the pattern continues with 0 CAPE and 0 surface-based CAPE in the machine learning forecast. The 0 to 6 km shear strengthens slightly to 29 meters per second, and the lifted condensation level rises to 882 meters above ground. The 700 to 500 millibar lapse rate of 5.5 degrees Celsius per kilometer is marginally steep but insufficient without moisture and instability. The ship index, supercell composite parameter, and significant tornado parameter all remain at 0. The storm mode forecast is subconvective, meaning conditions do not support thunderstorm development. The threat assessment shows conditional language. Any storms that did manage to form would face favorable shear for organization, but initiation is highly unlikely. The hodograph for Adelaide shows impressive wind shear despite the lack of instability. The 0 to 12 km wind profile is displayed in colors from purple at the surface through blue, green, and yellow aloft. We are seeing strong directional and speed shear with winds veering through the column. The 0 to 6 km shear measures 34 meters per second, which is significant. Storm relative helicity in the 0 to 1 km layer is 114 meters squared per second squared, and in the 0 to 3 km layer it reaches 341. The bunker's right mover storm motion vector, shown by the red star, points toward the east-southeast, meaning if supercells were to develop they would track in that direction. The left mover vector points north-northeast. This is a classic severe weather shear profile, but without CAPE to work with, it's like having a racetrack with no cars. The Bruntweisler frequency profile, or n-squared profile, shows atmospheric stability throughout the vertical column. This analysis reveals where the atmosphere resists vertical motion. The profile confirms the stable stratification we've been seeing, with positive buoyancy frequency indicating layers that suppress convective overturning. The lack of significant negative n-squared values means there are no strongly unstable layers to support rising motion. This reinforces our diagnosis of a subconvective environment, where parcels simply will not accelerate upward even if lifted. Bottom line for Adelaide, despite favorable wind shear, the atmosphere completely lacks the instability needed for thunderstorm development. Always consult the Bureau of Meteorology for official warnings and forecasts. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.